Okay, good morning, everyone. Let's get started. Hopefully, everyone has enjoyed your great fall break. So, but here we just want to give you a reminder that our homework 2 will be due on this Friday. And I've seen a few requests for the help during the fall break. I would love to help, but unfortunately, our TAs need their fall break as well. So if you have yet started and do need some help, please fully leverage our office hour. We got office hour every weekday, and hopefully we can help you as much as possible. And you can also post their questions on Canvas. I saw the few discussions on Canvas, but not as active and intensive as previous years. So you're encouraged to discuss or share any of your concerns or confusing stuff about homework, about anything in the Canvas discussion post. You can, just don't post your code. You're just saying, okay, I'm a little bit confused about that, and then I will try to answer you as soon as possible. But I think today, since starting from this week, if you're still, if some of you are still like, hurry to finish the homework 2 and testing all the kind of stuff, if you have any problem, just stop by the office hour, right? And especially if you feel like your code doesn't work, why it doesn't generate the expected results, right? Stop by the office hour. Okay, so today we're gonna continue with the perceptron algorithm. So to refresh our mind, right? So we're gonna go back to the perceptron algorithm framework itself. Right? So perceptron algorithm is the first linear classifier learning algorithm we talked about. So it is essentially an online algorithm. So basically, you can view that, okay, you're gonna stream your training data into an algorithm one by one, right? You might want to stream your data set many passes, right? Not just one pass. So we're assuming that we got a sequence of training examples, x1, y1, x2, y2, and so on. And your label is either -1 or 1. At the beginning, we initialize our model parameters. So here's the weight vector as a 0 vector. So here, the weight vector includes the bias parameter. Right? So it's an augmented version. So that means each xi is also augmented with a constant feature 1. Right? Everyone's clear about this? Right. And then we're going to go through each training example, right? One by one. Right? For every training example, xi, yi, I'm going to use my current weight vector to make prediction, right? We know that the rule of doing linear classification is as follows, right? We first calculate this so-called classification score, right? The score is the dot product between the weight vector and the feature vector. Then we just look at the sign. Right? And if the sign is 1, our prediction is 1. Otherwise, the prediction is -1. Right? Then, if your prediction is correct, what shall we do? Nothing, right? So that means, okay, if your classifier, your current classifier can correctly predict the incoming training example, that's fine. You don't need to do anything. We only update our model when you make a wrong prediction. Right? So that's why you have this if condition, right? If your prediction is different from the true label, you're going to follow this rule to update your weight vector, right? So you add the current weight vector WT, this guy. So here R is a small positive constant. We call the learning rate, right? So by default, you can simply set it to be 1, right? And you multiply the feature vector xi with the label yi. So you can imagine that yi is either 1 or -1, right? I mean, that means, okay, you're gonna either add r times xi to wt or subtract wt by this r xi, right? And you finish this update. Then you look at next example. Make a prediction and check if your prediction is correct or not. And if this wrong, if the prediction is wrong, then you follow the same rule to do the update, right? Just keep doing this until you finish the passing of those set of training examples. Say 2 passes, 3 passes, or maximum number of the passes you set. Okay? Then you return the final weight vector. So any question regarding the algorithm framework? No, we have. Yes, 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 yes. This is just for convenience. Yeah, that means, as we just mentioned, right? So each feature vector xi has already been appended a constant feature 1, right? So that means the corresponding weight vector, there will be one element corresponds to the last term. Just to make sure, although when we write down the prediction, right, we just do dot product, right? We do not explicitly write out the bias term, but just keeping in mind there is always a bias term inside that. Okay. Any other question? Yeah, this is really, really important. That's why we keep repeating this, introducing this algorithm, because in your homework 3, you're gonna implement this perception algorithm. Okay. And according to the true label for each example, right? We'll have like 2 updating rules, right? So if you make prediction on a positive, if you make a wrong prediction on a positive example, that means yi is 1. So your updated rule will be here, right? So add r times the feature vector to wt. If you make a wrong prediction on the negative example, that means yi is -1, right? Then your updating rule becomes subtracting wt by r times xi, right? So in the last lecture, we have explained why doing so is reasonable, right? So we're not gonna go through that in too much details, but just the intuition is that, okay, in whichever case, right, your wrong prediction is mainly due to either your classification score is too large or too small, right? For example, if you make wrong prediction on the positive example, the reason you made a mistake is that your classification score is too small. It's below 0, right? So you can find out by following this updating rule here, you actually increasing your classification score. That's the right direction, right? Because your mistake was due to the too small value, right? If I want to correct mistake, at least I should increase my score. So similarly, you can justify your update when you make a mistake on an active example, right? It's the same thing. We also have shared some geometric intuition about updating rule, right? Which I'm not gonna repeat this, right? But it will be very helpful if you can follow, read those slides, right? After classes will give you a more concrete sense why this is reasonable, right? And then we talk about the behaviors, the learning behaviors of perception, right? So that will introduce us the so-called perception mystic bound. Right? So basically, we can summarize the behavior of perception in 2 aspects. First, if your data set is linearly separable, then perception is guaranteed to converge. Converge meaning that you will be able to correctly classify every training example. There won't be any update after a finite number of updates. right? And the second theorem is called cycling theorem. This applies to non-linearly separable data, right? If your data is not linearly separable, then the perceptron cannot converge. And if you keep running it, I mean, you don't force your perception algorithm to stop after, say, a certain number of iterations, or you just keep running it, you'll find that eventually the algorithm will enter into an infinite loop. So it is going to go through a set of weight vectors, cycling through them. Okay. That's called cycling theorem, right? So we'll focus on this convergence theorem because it will introduce, it will reflect some important insights about perception algorithm and also introduce an important concept. So the first concept is called margin. Right? So bear with me. I have to review this. We have to review this margin concept again because this is a key concept of the following topic, like support vector machine. So when we talk about margin, we mean to say this is some property for a separating hyperplane to a data set. So that means first, the data set itself is linearly separable. So that means, okay, that means this hyperplane can separate the positive examples from the negative examples in this data set, right? So yeah, please keep that in your mind, right? If the hyperplane does not separate this data set, then it doesn't have margin, right? Then we define margin as the distance between the nearest data point to this hyperplane and the hyperplane. So here, for this particular example, you can see that the margin actually is distance between this black or positive example and the hyperplane, right? So any question regarding the definition of margin? Okay, and then we can extend the definition of margin to the margin for a data set. So what does it mean for margin of a data set? So first, we need to make sure that, okay, this data set is still linearly separable, right? If the data set is not linearly separable, it doesn't have any margin. And then we know that we could have many different separating hyperplanes, right? You might have like infinitely many separating hyperplanes. So the margin of the data set is the margin of a separating hyperplane, which has the maximum margin. Like going back to this data set again, right? So you can imagine like we can draw many separating hyperplanes, right? If we want to find a hyperplane whose margin is the largest, then we define this largest margin as the margin of the whole data set. Does it make sense? Any question? Okay, so you can imagine like I can draw one separating hyperplane like this, right? I have margin. I can draw another separating hyperplane here. I got another margin, right? I just look at which separating hyperplane has the largest margin. I use that margin as the definition of the margin for this whole data set. Okay. So what does this mean, right? What does this data set margin reflect, right? It actually reflects the separability of the data set, right? Reflects how hard you're going to train a linear classifier to discriminate positive and negative examples in this data set, right? Any questions so far? calculate this margin. How can we calculate this? Slope. Oh, yeah. I think I understand point. Your question, my rephrase should be the same, right? So how can we calculate the slope? Oh, this is the next topic, right? So actually, when we talk about support vector machines, the goal is to find a hypothesis. Well, here it will be a line or hyperplane which maximizes the margin. Right? Then it reduces to some optimization problem. You see that the naive optimization will be some bi-level optimization problem that is too complicated. Then we're gonna leverage some insight about linear classifiers and then convert it into a single level maximization problem with some additional constraints. And we have a kind of series of chains of logic to doing the reasoning and optimization. But here we just want to introduce the idea here, right, to give you some sense. Any other question? No, when we talk about margin, I mean the data set must be linear separable. Even there's some like points which are violated by linear classifiers, then we can also see that linear classifier has margin. And so yeah, later when we talk about support vector machines, you will see that actually the learning will be automatically like for those nonlinear data set, right? The learning will be automatically pick up some points from data set, just kick them out. Then for the remaining data points, which we believe is linear separable, you want to find out a linear classifier whose margin is largest. So that's some kind of elastic mechanism to do this trade-off. Any other question? Okay, great. Then we shall like review the definition of distance, right? So we know that if we write down a linear equation to be zero, from geometric point of view, it represents a hyperplane, right? And then in a vector space, we know that any point in a vector space can be represented by vector, right? So we can calculate the distance between this point x0 and hyperplane h following this formula, right? So the formula is very straightforward. You just evaluate the left-hand side of this equation, right? Take the absolute value because distance is always non-negative. Then divide it by the norm of the weight vector w. This is just the formula, right? And I believe everyone is able to prove that because we have learned that long time ago. And then if we consider the augmented feature space, meaning that we have introduced a constant feature 1 into X, and so that W contains a bias term. So our equations will be like this, right? And then for any distance x0, the distance between x0 and h will be like this. Right? And remember, x0 here contains a constant 1 as well. And if we will h as a separating hyperplane or classification boundary, right? If this classification boundary can correctly predict the label of x0, assume that it has a label, right? So then we can represent the numerator by y0 times w transpose x0. This is always non-negative. Why? Why we can replace this absolute value by just label multiplying with the classification score. Any other supplement? Yeah. So remember, this is an important trick. We're gonna use that again and again, right? So basically, if your W correctly classified 0, so that means the sign of the score will be the same as the label, right? So if your prediction, if your label is positive, meaning Y0 is 1, your score must be positive as well. So the product will be positive as well, right? If your Y0 is negative, so -1, right? When you make a correct prediction, your score will be negative as well. So when you multiply them together, you still got a positive value. That's why in that case, you can simply replace the absolute value by this product. If further W is a unit vector, then the distance is simply this, right? In that case, we can now use this to calculate distance. Here we are assuming that, okay, your W can correctly predict the label of X0. Okay. Any other question? So yeah, further, if we assume that W is normalized, that means W is unit vector, we know that this denominator is simply 1, right? Then the distance will be simply Y0 W transpose X0. Yeah, just keep that in your mind, right? So now we can take a look at the Mies-Bond theorem, right? So what does Mies-Bond theorem tell us, right? So assume that we got a sequence of training examples, right? For every feature vector xi, we assume its norm is less than or equal to some big R. So it means the length of each feature vector is upper bounded by R, right? A label is either -1 or +1, right? And here we're assuming all the feature vectors are augmented with constant 1, right? And second, we assume that the data set is linearly separable. And there exists some unit vector such that for some gamma, positive gamma, we have this guy always no less than gamma. So what does this mean? What does the second condition reflect? Yeah, separable. Yeah, this is first. Yeah, that's the first implication, right? So what's the second? So what does the left-hand side mean? Distance, yeah. And you want to see something? And yeah, distance. And then yeah, from hyperplane. Yeah. So what does this inequality mean, right? We say, okay, for every training example xi, yi, we got this one. We got this inequality. What does it reflect? Yeah, minimum distance. So what does minimum distance mean? Yes, the margin, right? Yeah. So basically says, okay, we assume that the data set is not only linear separable, but we know that there exists some separating hyperplane, right? And the distance between every training point, example in this data set, and this separating hyperplane is no less than gamma. So that means the margin is gamma, right? Then we can claim that the perception algorithm will make at most R over gamma square mistakes on the training sequence. So basically just keep running your perception algorithm, you will find that after at most RO or gamma square updates. Remember, perceptron only make update when it makes mistakes, right? So only after at most RO or gamma square updates, the perceptron algorithm will be able to correctly classify every training example. That means it converges. That's what this Misty-Bound theorem tells us. So any question regarding the understanding of the statement of theorem? Okay, great. So the first precondition, like the length of each input feature vector is upper bounded by R. It's very easy to find, right? Because we can just look at the length of each input feature vector and find the maximum. We find this R, right? And the second assumption reflects that, okay, the data is linearly separable, and you assume that there exists some separating hyperplane whose margin is gamma. Right? And we actually mentioned that in the last lecture. Right? Someone might have a question, right? So why should we introduce assume the existence of unit vector? Right? Why not just assuming, okay, there will be a separating hyperplane whose weight vector is just W and blah, 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 right? So the reason we assume there exists a unit vector is simply because of the convenience. You can definitely assume, okay, there's a vector U and such that its marginless is no less than gamma, but you have to rescue gamma in the Misty bound. And this will be the final Misty bound like this. Of course, it will be a little more tedious. And later we'll ask you in the homework to show that if we do not assume a unit vector, that means the norm of U is not 1, and how do you prove the Misty bound? Okay, so the Misty bound theorem can be very roughly summarized as, okay, suppose we have a binary classification data set with n-dimensional inputs, and if data is linearly separable, then the perceptron algorithm will find a separating hyperplane after making a finite number of mistakes. That's what roughly the Misty bound theorem tells us. Okay, any question so far before we proceed to the proof step? Everyone's comfortable? Okay. So yeah, so now let us look at the proof, right? So here is the key steps of the perceptron, right? Every time we assume that we're going to receive an input xi, yi. If our prediction is wrong, we're going to follow this rule to update. And here we assume the learning rate R is someplace 1. Right? We initialize all the whole weight vector as 0. Right? And two important preconditions. The first condition is that all the training examples are contained in a ball of size R. Right? That basically means the length of the feature vector is upper bounded by R. And we assume that the training data is separable by some unit vector U with margin gamma. When we translate to math, it will be for every I, we have this yi U transpose xi, no less than gamma, right? So let's see how we prove this theorem, right? Actually went through part of it during our last lecture before the 4 break. So we're gonna use 3 steps. The first 2 steps will prove 2 inequalities. The third step will just piece this inequality together, then you can derive a bound of the number of mistakes. Okay? So in the step 1, we're gonna use induction to show that after T mistakes or T updates, we have U transpose WT. WT is the current weight vector of our model parameters after T mistakes or T updates, right? Is no less than T gamma, right? And we're going to use induction, right? Induction means that, okay, we're going to assuming as step T, this is correct. Then can we see if we can extrapolate the same conclusion to step T plus one, right? That's the induction, right? So let us assume, okay, at step T, we got this inequality to be correct, right? We want to check at T plus one, meaning that after T plus one mistakes, right? Do we still have this inequality, right? That means we need to check U transpose WT plus one, right? We know that after T plus one's mistake, right, we have to update our model parameters, right? Following this rule. So it means WT plus one equals to WT plus YI XI, right? So now you just replace WT plus one by the right-hand side here, right? We can see that U transpose WT plus one equals to U transpose WT plus YI U transpose XI. Right? This one, following our second precondition, we know that this is the distance between XI and U, right? And because U has correctly predicted the label of XI, so we know that this guy is no less than gamma, right? So we got U transpose WT plus gamma, right? And meanwhile, from induction assumption, we know that U transpose WT is bigger or equal to T times gamma, right? So you merge this gamma, you got T plus one gamma on the right-hand side. Okay. Then your induction step is correct, right? It's done. So what's the next step? You just check the initial condition, right? You just check if when T is 0, as from very beginning, if this is correct, right? From very beginning, that means T equals to 0. What is the left-hand side? 0, right? Because WT is initialized at 0. And what is the right-hand side? 0 as well, because T is 0, right? So because W0 is 0, so that means U transpose W0 is 0, right? So T is 0, so right hand is 0. So at beginning, when T is 0, we know that this inequality is correct, right? And then following our previous induction steps, we know that for every step T, you're gonna extrapolate to T plus one, right? You can do this forever and ever. Sorry. So in this way, we have proved the first claim. Any questions so far? Okay. So then let us look at the second claim, right? The second claim is that after T mistakes or updates, right, the square norm of WT is upper bounded by T times R squared. So this big R, remember, is upper bound of the length of the input feature vectors, right? We will still use induction to show this is correct, right? Again, we first assume at step T, this is correct, right? We're gonna see when we extrapolate to T plus one, if this is still correct. That means we need to check the square norm of WT plus one. Right? Again, because WT plus one is WT plus YI XI, right? You just substitute this guy for WT plus one, right? You take the square of the norm. This is essential to expand the quadratic term, right? We can expand it into 3 terms. The square norm of WT, the square norm of YI XI, okay? YI is either 1 or minus 1, so square norm is just gone, right? It's just 1, right? And then you got a cross term, which is 2 YI WT transpose XI, right? Everyone's comfortable? Or is this too simple? Okay. And then we got 2 observations, right? First, the rightmost term, right? Xi norm square. We know that because Xi its length is less than or equal to R. So this guy is upper bounded by R squared, right? So this guy is upper bounded by R squared, right? And this one, we need some observation, right? Because WT plus 1 is obtained when you make a mistake, right? So that means when you see X and Y, you make a mistake. That make you update your weight vector. So when you make a mistake, what's the sign of this guy? Negative, right? Because the sign of the score and the label is mismatched, right? So, sorry, it will be less than 0. So that means the right hand side will upper bounded by R squared here, right? Plus WT square norm, right? And this guy is less than 0. So it is upper bounded by this guy plus 0, right? So from the induction assumption, we know that square norm of WT is upper bounded by TR squared, right? So merge this R squared, we're going to get the upper bound of T plus 1 R squared, right? So we'll finish the proof of the induction step. And what's the second step? What's the second step? Okay. We show the induction. After we show the induction is correct, what's the next step? Proof what? Yeah, base case, right? So base case will be when T is 0, right? When T is 0, we know that WT is 0. So left hand side is 0. The right hand side is also 0. So the base case is correct. Then following our induction steps, we know that it can extrapolate to step 1, 2, 3, 4, 5, 6 until infinite, right? So any question regarding the proof? Okay. So now after now we got 2 claims, right? After 2 claims, we have 2 conclusions. First, we know that after T mistakes or updates, we got U transpose WT is no less than or equal to T gamma. Okay. And after T mistakes, we got the square norm of WT is upper bounded by T big R squared. Okay. The third step will just piece these 2 inequalities together. Right? How can we do that? We start from the second claim. Right? If you just reverse the inequality, right? Take a square root on both sides, we got R times square root of D is no less than the norm of WT, right? And next, we're going to use a very important inequality. It's called Cauchy-Squarz inequality. It basically says WT is norm is no less than U transpose WT, dot product between U and WT. How can I show this, right? Consider 2 vectors, right? U and WT. We know that the cosine of the angle between the 2 vectors, U and WT, is the dot product divided by the norm of U and the norm of WT. Right? This is the definition of cosine. Right? And because our precondition assumes that, okay, your norm of U is 1, right? It's a unit vector. So this guy is 1. Okay? And because the cosine is always less than or equal to 1. Right? So that means U transpose WT is always less than or equal to the norm of WT. And this is called a Cauchy-Squarz inequality. And once we obtain this result, you can see that it connects back to the first claim we just made, right? And now we just write down the right-hand side of the first claim, right? We now have this long inequality. But actually, we only need the head and the tail, right? We just pick them out, right? We got r square root of t is no less than t times gamma, right? You just solve that inequality in terms of t. You immediately derive that the number of mistakes t upper bounded by r squared over gamma squared. So now we can see the whole procedure, right? You got two claims, right? Both claims are proved by induction, right? And then you apply Cauchy-Squarz inequality, you connect the two claims, you find a integral inequality regarding the number of mistakes of t, right? Then you solve that inequality regarding t, you derive an upper bound of number of mistakes t. It bounds the total number of mistakes. Okay, any questions so far? Okay, so hopefully after the class you can go through this several slides to get familiar with this proof as well, because in our homework you're gonna be requested to prove a slight variant of this mistake bound. And the proof steps are exactly the same, but you need to make some slight modification. Okay. So now let us review again the mistake bound theorem, right? It just tells that, okay, if I have got a sequence of training examples, every training input vector, its length is upper bounded by R, and the data set is linearly separable. And there exists some unit vector U, whose margin is gamma. Then we'll claim that you run the perceptron algorithm. It will make at most R or gamma squared mistakes on the training sequence until convergence. So an interesting question will be, do we have some geometric interpretation of this bound? Right? So here we consider an exemplar data set, right? We got positive and negative examples, right? We know this is linearly separable. And first, we can find an upper bound of the norm of the input feature vectors. Of course, you can just find out the point which is furthest from the origin, right? So you know that draw a circle or sphere with the radius r. All the training examples are contained inside this bound, right? And then if we can find out a separating hyperplane whose margin is gamma, meaning that minimum distance between the closest point and the hyperplane is gamma, then we claim that you run your perceptron, right? The number of mistakes your perceptron will make at most will be r squared or gamma squared, which is just the ratio between this ball radius r over this minimum distance gamma and take square. Any questions so far? Everyone's comfortable? So I want to ask a question. If you run the perceptron, will you find out separating hyperplane which overlaps with this guy? No, right? That's good, right? That's a very important point. So this gamma and associate separating hyperplane, it just serve as the terms in the upper bound. It doesn't mean that your perceptron will converge to the same separating hyperplane. It might converge to a totally different separating hyperplane. Right? It just tells you that, okay, no matter how you shuffle your training examples and stream that into your perceptron, right? It will just make at most this many of mistakes or updates until it finds a separating hyperplane. Any other question? Okay, great. Yeah, looks like everyone feels comfortable. It's not as many questions as previous students, right? Okay. So to deepen our understanding about the perception mistake bound, I want to do a few exercises, right? For example, if you are asked to learn a linear classifier to separate the Boolean input feature vectors, right? How can we construct R and gamma and then construct the upper bound? Right? This will help us to understand the behaviors of perception. Right? For example, how many mistakes will the perception algorithm make for the k disjunctions with n attributes? Right? And the training set are all Boolean feature vectors in the instance space. Let us do some practice. Suppose this is our target function, right? Or label. The label, the ground truth label is obtained by the disjunction of this n Boolean features, right? So want to know that, okay, suppose you are given all possible Boolean feature vectors, that will be 2 to the power of n feature vectors, right? At most, how many updates will you get a good separating hyperplane by running a perception? Right? First, according to this bound, right, we want to find R, right? We want to find the upper bound of the length of the feature vectors, right? So what is the upper bound? Yeah, I write the result here, right? But can we explain why we can set this guy as the upper bound? Can I see it again? No, R is not. R is the maximum length of the feature vectors, right? And our feature vectors are just Boolean feature vectors, right? Which feature vector has the largest length? Yeah, checked all everything, right? So which one is the longest length? It is the longest vector. Well, we don't have like a vector that has an infinite length, right? And here we're assuming our feature vectors are just Boolean vectors. Every element is either 1 or 0, right? And then which vector has the longest? Yes, right? So remember, if you go back to here, right? The R is the maximum length of those feature vectors. Or in other words, you can find out a point which is furthest from the origin, right? Yeah, R is the radius. Right? That's why we're gonna take a look at a data point who is the farthest from the origin, right? And in our case, like here, we're talking about the Boolean function, right? All the feature vectors are Boolean feature vectors, right? They are either 1 or 0. So I want to ask, right, which feature vector is the longest one? No, 0 or 1. Every feature is either 0 or 1. Yeah, all the ones will be, right? All the ones will be, I mean, the vector with all ones will have the longest length, right? Does it make sense? Maybe I can. Yeah, the length of each vector. Oh, the length. The definition of length. Okay. So let me write down a vector, right? So let me just random write down vector. So is h1 say h say hn, right? So what's the definition of length of this vector? No, it's not like that. Yeah, like a norm. Yeah, it's just the summation of h1 squared plus h2 squared plus dot 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 plus hn squared, right? Right. Yeah. Now we know that because in our case, those are bounded features, right? Of course, when all those elements are ones, you got the longest length, right? So, and here we plus one. Why do we plus one? No, it's not like. Yeah, it's because it's an augmented feature, right? Yeah. Remember when we applied the Mies-Bond theorem, right? The first precondition is that okay, we need to assume that all the feature vectors have already been augmented by constant, right? Remember, this is our precondition. So when we talk about this, right? All the feature vectors are augmented with constant one, right? And then we can see, okay, this guy is a distance, right? Otherwise, the distance should be, you have to explicitly write out the bias term B, right? Just, yeah, just be careful when we apply that, right? Y is plus one. Okay. So the feature vector is augmented with one, right? So you can imagine that the augmented version, let me denote it by bar, right? So this should be h1 to hn and then additional constant one, right? So know that, okay, all h1, h2 to hn are ones. Your whole augmented feature vector, its norm is the largest, right? Yes. Yeah. You shouldn't say B is just a constant feature one because B is the parameter. It's inside W. Yeah. And other problem. Okay. Yes. Yes, exactly. Yeah, that's our definition here. So just be careful. This is not length doesn't mean like the number of elements. Is our we follow the definition, the classical definition of the vectors, right? Okay. So now we can easily find out, okay, your R, right, which is just the radius of the circle or sphere which contain all the training examples, right? And step two, we're gonna find a separating hyperplane with non-zero margin, right? Remember, this is our theorem, right? Our theorem tells out, okay, if you can find a separating hyperplane unit vector and margin gamma, you can construct your Mistaken bound, right? So how can we find a separating hyperplane, right? From our previous discussion, we know that this is pretty straightforward, right? When conjunction is one, that means the summation is at least one. Okay. And then we can construct an equivalent linear classifier, x1 plus dot 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 plus xn minus 1 equals to 0, right? So now I want to ask, can we use that as a separating hyperplane and get a margin and calculate the bound? Yeah, this is separating hyperplane, right? This is, we have already discussed this example before, right? For this disjunction function, we can construct an equivalent linear classifier, which can correctly predict every possible n-dimensional Boolean feature vector, right? No, want to ask, if we can use this linear classifier to construct our Mystic bound. To answer this question, we need to first know, okay, what's the margin of this classification boundary or hyperplane? 1. Why is 1? Yeah, I think you're thinking right direction, but the result is not correct. Margin is the minimum distance, right? Which point gives you the minimum distance? All the feature vectors are zeros? Really? Are you sure? All zero. What? Yeah, that will give you one distance, right? But unfortunately, it won't be the point which is closest to this hyperplane. Which feature vector is closest to this hyperplane? Remember, our feature vector are all possible Boolean feature vectors, right? You can pick any element in your feature vector to be 0 or 1. So who can tell me which point or which set of points can give you the smallest distance to the hyperplane? Example is negative. Example negative. Yeah, example is negative. That means all x1 to xn are 0, right? Yeah, that will give you distance, but it's not the minimum distance. Any thought? Yes. There could be some points right on the plane. What kind of points? What kind of points will be right on the plane? Yes. So what kind of points can satisfy this equality? What? No, not unit vectors. Yes. But you're right. Yeah, unit vectors. Yeah, yes. Unit single ones are unit vectors as well. Yeah. Okay. So now we can find some counterexamples, right? If you just pick up one feature to be 1 and set all the other features to be 0, left-hand side is simply 0, right? That means that points will stay on the hyperplane. Why? Because distance 0. Right? Yeah, if you look at distance formula, right? We talked about them before. This is just the evaluation of the left-hand side, right? -1 and divided by the norm of the weight vector, right? And here, a normal weight vector will be just 1, 1, 1, 1, 1, and ones, right? So if you can make this equation, if you can satisfy this equation, that means your distance to this hyperplane is 0. That means your points are staying on a hyperplane. You can see this, right? No, I never see margin should be greater than, should be no less than 0. Yeah. So if we use a figure to show this, we actually can see that these points, or at most, or at least endpoints will stay right on the hyperplane, right? And then what's the margin? You do not get what? This is just one instance. Yeah, you got all possible instance of this n Boolean feature, right? And you can definitely pick up any vector, right? And I just tell you, okay, among these 2 to the power of n possible feature vectors, I can find at least one feature vector which stays on the hyperplane. One hyperplane passing through n positive examples, right? Because you can set the first feature to be 1, all the other 0, or you can set the first to be 0, and the second one, all the other 0, right? You actually have you got n features, you got n such vectors which stay right on the hyperplane. Okay. So now, what's the margin? 0, right? Remember, margin means the distance between the closest point and the hyperplane, right? So that means your margin is 0, your gamma is 0. And what is your upper bound? Infinity, right? Well, you can say undefined, or you can say infinity. Both are fine, but basically that means that doesn't mean anything, right? We want some finite bound, right? You can say, okay, the number of mistakes you make is less than or equal to infinity, so it's meaningless, right? We want some more meaningful upper bound. That means yeah, we'll get to that point in a minute. So the root reason of this is that this separating hyperplane will give you 0 margin. So your construction of the hyperbound, the upper bound is not very meaningful, right? Then what shall we do? We should choose another separating hyperplane with non-zero margin, right? And you got non-zero margin, of course, you can construct much more meaningful upper bound. Okay. So actually, there could be numerous ways to find an alternative separating hyperplane. And here I just give you a very simple alternative. That is, I just move this line a little bit so that I switch 1 to half here. So see that this will still be a separating hyperplane. Why? What? Can I say it again? Separating. I mean, this line will perfectly separate all the positive and negative examples. Why? Yeah. So first, we need to check, okay, if it can correctly predict all the positive examples and all the negative example, right? There is only one positive example. Oh, sorry, there's only one negative example, right? What is the negative example? It's a disjunction, right? When the disjunction is 0. Yeah, they're all zeros, right? When it is all zeros, we only have one negative example, right? Because as long as one single element about those n features is 1, then it's positive, right? So you can see that first for the only single negative example, That means all x1 to xn are 0. So what does the left-hand side? What is the left-hand side? Negative, right? Of course, it correctly predicts because sign is -1. And how about all the positive examples? Yeah, at least 1/2, right? Because as long as this one equals to 1, that means at least one feature will be 1, right? Then you evaluate the left-hand side. That means the left-hand side will be at least half, right? They're always positive, right? And then what is margin? Yeah, someone has pointed out it's actually just half, right? What's the margin? Which point is the closest to this hyperplane? Okay. Yeah, that one. What is that one? Yeah, either the negative example, right? All zeros, right? Or the examples only contains one element as 1, right? Does it make sense? Right? Because if it contains 2 ones, right, your distance will be bigger than half. Right? If your x1 to xn like contains only ones, your distance will be half, right? And divided by some norm, right? And or if your x1 to xn are all zeros, your distance will be half divided by some norm, right? So now we can see that we find out a better separating hyperplane, right? And because no points will lie on the boundary, we will get a non-trivial margin, which is half over n plus 1/4. Right? It's just norm, right? And now you got a u vector because you have to normalize your u vector, right? It's a unit vector. You got a gamma, and then you just construct your upper bound, which is r squared over gamma squared, right? And that's it. Any questions so far? Yeah, I mean, if you feel a little bit uncomfortable or does not feel like you fully catch up what we talk about, just look at the slides again. Right? It's not hard. I just want to use some detailed example to show how we can deepen on our understanding about this mistake bound theorem. And in our homework, there will be a few practices very similar to this one. It's not necessarily disjunction. I'm asking you to do the conjunction and to find the separating hyperplane, to construct R, to construct a non-zero gamma, and construct bound. Okay, so regarding the theorem of mistake bound theorem, right? What do you need to know? First, what is the perceptron mistake bound? Second, how to prove that. So the last portion I want to talk about perceptron is the practical variance. Okay? So the algorithm framework we introduced from the beginning is just the simplest one, right? In practice, you need to consider, okay, if your data is linearly separable, right? How do you make your algorithm more robust, right? That is about the variance, right? So we'll mainly talk about two variants. One is called margin perceptron. The other is called voting and average. You see that the voting average is more like ensemble learning. We will have like a very smart strategy to store a set of linear classifiers, then combine their prediction with some votes. It's very similar to boosting algorithm. Okay. So first, this is the standard algorithm, right? We initialize our model parameters W, lead vector, to be 0. Then we go through big T epochs. Inside each epoch, we're going to shuffle the data, right, according to some random order, right? Then we're going to stream each training example and look at if your current prediction is correct or not, right? If it's incorrect, remember, we can use this inequality to check if your prediction is incorrect, right? And then we're gonna run this update. Right? So here, we need to set a hyperparameter big T, right? How many epochs you want to run, right? This, unfortunately, there's no golden standard how to set that. You have to tune it according to your specific problem. Right? And secondly, and for convenience, right, we just use this inequality to check if this is an error, right? So we know that when we make correct prediction, this guy will be positive, right? Otherwise, it will be negative. And once you finish all the big T epochs, you got a V vector. You just make prediction according to the sign of the score, right? And this is standard algorithm. So the first version, the first variant we want to talk about is called margin perception. So now we go back to the concept of the margin. So we can see that given this example data set, right? Positive and negative examples are definitely separable. That means we have like many, perhaps numerous separating hyperplanes, right? Now I just random draw two hyperplanes, H1 and H2. I want to ask you guys, which one do you believe will generalize better? H1. Why do you think H1 is better? Because it has a larger margin. But why when we have a larger margin, we should have a better generalization performance? Okay, let me summarize your thought because it exhibits like larger separation, right? Okay, what's your thought? Can be more explicit. Let me catch your main point. Okay. Yeah. Okay. I think you two kind of like is going to touch the major intuition I want to express. Right? Yep. Intuitively, when we say, okay, this hyperplane has larger margin, that means, okay, it is far away from both positive examples, negative examples, it exhibits larger separation, right? But I want to think about one step further, right? So why exhibiting better separation will lead to better generalization performance? Yeah, why it can give you less mistakes? There's more room for error. But regarding of your point, actually it's not rigorous to see that. Because, well, you could see, so a larger margin, right? You can construct a smaller misty bound, right? But doesn't mean that your learned perception will perform better, right? Because this is if you use H1, H2, their margins to construct upper bound, it just tell you the upper bound, right? It just it doesn't reflect any generalization performance. Yeah, but here we want to give a little bit more analysis about your intuition from your guys, right? Your intuition is right? But we just need a little bit analysis, right? So when we see the clusters of training examples, those regions which contains a cluster of training examples actually reflect the high density regions of those type of examples, right? Why? Because according to probability theory, when examples shows up there, that means it has higher likelihood to show up, right? So that means this portion and this portion, these are places where you got a high chance to meet the corresponding examples, right? For example, here, you have a higher chance to see positive examples. And here you have a higher chance to see negative examples. Those are representing high density regions, right? And correspondingly, the further away from the training examples are, the smaller or lower the density regions of those positive and negative examples. And what's the benefit if you place your separating hyperplane further away from those high density regions? You actually lower the risk of misclassification. Why? Right? We can take a look at H2, right? H2 has a much smaller margin. That means it is much closer to the training set, right? And it's much closer to the training set. It means that it is highly likely to pass through the high density regions. So you can see that this part of H2 pass through the high density regions for positive examples. That means on the other side, right, they'll make a lot of mistakes here, right? Because you can view, like you can see, you have a very large chance to see positive examples on the other side, which H2 will predict as negative, right? And similarly, you can see H2 is also close to the negative examples, right? It passes through the negative high density region for the negative examples. Then it has a high chance to misclassify the negative examples on the other side. So you can see the point, right? If you're getting closer to the training data set or training examples, that means that you are more likely to pass through the high density regions of those examples of different labels. And that means you'll have a higher risk to misclassify the examples. Why? Because you pass through them, right? On one side, you predict them correct. On the other side, you predict them wrong. On the other hand, if you set your hyperplane, the position to be further away from both positive and negative training examples, that means, okay, you're pass through the low density regions. It is highly unlikely that you're going to see a positive example here. So you make a mistake. Or unlikely you see a negative example here, so that you make mistakes, right? That's the benefit of doing large margin classifier, right? Because you put your decision boundary on low density regions, you reduce the risk of misclassification. And we will see this idea again and again. When we talk about support vector machines, we'll see that essentially support vector machines trying to find out a hyperplane which has the largest margin for the data set. Okay, let's stop here today and see you on Thursday.